Good evening, ladies and gentlemen. Welcome to our first installment of our flipped classroom lecture. The first one we're going to be doing is on section 13.3, finding probabilities with combinations. I just want to take a moment to tell you how to do this because, well, this is our first time. I'm going to be making mistakes. You're allowed to make mistakes as well. As you listen, make sure that you're taking notes just as you would in class. There's actually going to be a few points during most presentations, if not all, where I'm going to ask you to either pause and work out a problem or pause and ask a question to yourself. Give yourself that time to answer that question. I'm not going to sit there and leave a big blank space in the video because I want people to be able to go through these videos as fast as possible. So use the pause and the play button just to pause so that you can either work out the problem or answer the question, whatever I ask you to do, and then go on with the video. If you need to work out an example in addition to what I'm doing on the screen, feel free to do so. I would make a lot of use of that pause button just so you can get the most out of these videos. Remember, you should be coming to class ready to go, ready to do your homework, fully prepared, and we'll try to make class time more fun with more activities, which works well in this probability unit. So, the first section that we're going to do here is 13.3, and it is finding the probabilities with something called a combination, which is slightly different than a permutation. The first thing I'd like to ask you to do is I would like you to find all the permutations, what you know how to do, or all the different combinations, choosing any two of the letters A, B, C, or D. Go ahead, make that list, pause the video, and I'll be right back with you as soon as you hit play. Okay, there should be 12 of them. The way I made my table was I locked in the first letter and altered the second each time. So you get A, B, A, C, A, D, then B, A, B, C, B, D. Now the question that we're going to ask today is all those numbers up there, or all those letter combinations in orange here, are permutations, and each one is unique, and we still count those as permutations. But the question we're going to ask today is how many permutations are there if we say that order is not important? That is, if we say that DC is the same as CD here. My question then is, out of these 12, how many of those are unique if we say that order is not important? You can pause the video and ask that. I will sit here and start crossing stuff out. Take a guess as to how many you think are going to go away. Like I said, CD is the same as DC. I can start crossing off DB. I got BD over there. Actually, I shouldn't cross this one off. Hold on one second. I told you there's going to be mistakes. I'm only going to cross off the ones that I don't want. So DA is the same as AD. CD is going to survive. BC, same as CB. AC, same as AC over there. And finally, last and not least, but AB is the same as BA. So, there we have it. It cut our list in half. Now, the question is, will this always happen? If we say that order is not important, that is, the combinations that we're dealing with are the same as long as they contain the same letters or numbers or whatever it is, will that always reduce the number of permutations? That's my next question for you. So, should the number of combinations be more or less than the number of permutations? Pause the video, take a guess, and press play again. Okay, it should be the case that anytime that you're taking permutations, since order matters, they should be more unique, kind of like a Powerball ticket. It's just less likely that you're going to get the numbers in order. Actually, I'm not sure if that's how Powerball works, but spelling a word, how about? It's just less likely that you're going to jumble up a whole bunch of letters together to make a word. But if you took 3 letters, you might be able to make a word out of that regardless. So permutations more unique and more plentiful than combinations always, as long as you're talking about the same number of objects and the same number of objects that you're choosing. So just like permutations, we have a formula. Looks like that. You should have this in your notes. You're going to use this one over and over and over again. And it works the same way. It has this funky notation again where you have those subscripts. N stands for the number of objects, just like it did with the NPR formula. C stands for combinations rather than permutations. And R stands for the number of things that you're taking out of that group of objects, or the number of things that you're choosing. All in all, this notation over here stands for the number of combinations of n objects taken r at a time is given by this whole mess over here. And you'll notice that it is exactly the same as the permutation formula with the n factorial over n minus r factorial, but then you have an additional term down in the denominator, and that is indeed what makes this number that we're going to get smaller, because we're dividing the number of permutations we have by some number. So make sure you have that formula. I'll show you how to use it right here. So a very basic stripped down example right here. How many combinations are possible with 8 objects taken 3 at a time? Take a moment, try to assign n and r out of that statement right there. Pause the video, come back to it. Alright, this is what you should have got. You should have had 8 objects taking 3 at a time, so your n is 8, your r is 3. If you then take a look at that, once you plug it in, you'll go 8 factorial over 8 minus 3 factorial times 3 factorial. Again, this is kind of just plugging and chugging. You should be able to do this by hand. I am going to show you how to use it on a calculator, but you should be able to do it by hand. So up on top, you should have 8 factorial turns into 8 times 7 times 6 times 5 times 4, all the way down to 1. 8 minus 3 is 5, so you got 5 times 4 times 3 times 2 times 1. And then you've got 3 factorial, which is 3, 2, 1. So it looks like that. Then you'll notice that you have a 5, 4, 3, 2, 1 here, and you have a 5, 4, 3, 2, 1 here. So the 5, 4, 3, 2, 1s cancel out. Some people are very tempted to cancel out these 3, 2, 1s and 3, 2, 1s. That's fine, but just know that you also have a 4 and a 5 up here in common that you can also cancel out. If you get rid of all that stuff that's duplicated on the numerator and the denominator, all you have left up on top is 876 over 321. 8 times 7 times 6 happens to be 336. Divide that by 6 and you'll get 56. Now, that's how many combinations are possible with 8 objects, choosing any 3 of them and rearranging them. Notice that we got a whole number. You should never use this, you should never at the end of this formula get a decimal or a fraction or a non-whole number. So if you get something that is not a whole number, you've crossed off something or maybe done something wrong in the formula somewhere. It'll always work out to be a whole number, and that makes sense. You should not have 1.5 combinations of something. Okay? Here's a more realistic example. See if you can set this one up. Oh, there it is. Cheating for you already. But I gave you N, I gave you P, R. Try to figure out the formula. Try to get down to an answer for this one. A pizza chain offers 10 toppings from which to choose. They are currently running a special on 2 topping pizzas. How many different 2 topping pizzas are possible? And of course I did the wrong formula. So change all those 2's up in the description there to a 3 topping pizzas and 3 topping pizzas, and that should work. So let's go 10 toppings, 3 topping pizzas is what you're choosing. Go for it. Okay, if you do all that, you'll set up just like that. You get 10 factorial over 10 minus 3 factorial times 3 factorial. Get a big long expression up on top. 10 times 9 times 8 times 6, all the way down to 1. The 7 through 1 cancel each other out. You still have a 3, 2, 1 left over down on the bottom, and you still have 10, 9, 8 left over up on top. Do the math. You get 9 times 8 is 72, times 10 is 720, so you didn't actually need a calculator for that one. Divide that by 6, you should be able to do that without a calculator, for a total of 120 different combinations, or 120 different possible pizzas. Getting close. Okay, calculator. Your calculator can do this for you. On your TI 30iX, it'll fall under that same PRB button that is diagonal from the second key. However, I have this virtual calculator here that is the graphing calculator, and it's a little bit more fancy, but I can find the same menu under this math button right there, and if I scoot over to probability, you'll see an NPR, an NCR, and a factorial just like you have under the PRB button on your TI 30iX. If I scoot down to NCR, I can do combinations. Remember, that was permutations. The factorial was permutations, where you're just straight up choosing all of the things. So if I hit enter there, that'll give me NCR, and I forgot to enter how many objects I'm choosing, which was 10. And we'll go back to our formula here. We'll go probability, NCR, and we're choosing 3 toppings for our pizzas. We hit enter, and look at that, we get 120 as well. So your calculator does have this. You should be able to work some of these by hand. Remember, I can ask you some huge numbers where it might overload your calculator for you. Okay, so over the course of the next few days, we are going to be drawing out the distinctions between permutations and combinations. And basically the major difference is permutation, the order matters. So think of ordered pairs, think of spelling words, think of passwords, maybe choosing a team with positions. You can't just switch around a baseball team. You can't have any player play any position in any game of baseball. Whereas a combination is a little less stringent. 9-4 we do count as the same as 4-9, so the order does not matter. Think of pizza toppings, sandwich toppings, and maybe just making team members, where if you get a group of 4 people, it really doesn't matter in which order you arrange their names. There's still a group of just 4 people. That being said, with this little comparison right here, and you got the 2 formulas down there, question for you. A combination lock is a series of 3 numbers that will open your lock. Is that an example of a permutation or a combination? Take a moment, answer it, pause and play. Ironically, a combination lock, even though it has the word combination in it, is actually a permutation, because the order in which you dial the numbers matters. So unfortunately, this is not a good example to have in your head when you're trying to define combination to yourself. So the big question over the next couple days, when we're trying to figure out how many possibilities are available in our sample spaces for calculating probability, is, does the order matter? Okay, if the answer to that question is yes, you're going to go through the permutation formula. If the answer to that question is no, you're going to go through the combination formula. That is all I have for you tonight. I hope that I didn't go over my 10-minute budget. I'll see you shortly. I'll see you tomorrow. Have a great day.